today we're going to be talking about some of the, I don't know if you can say they're some of the most important things in computers, but some of the more important things that you never realize actually are a thing, if that makes sense. Interrupts and polling. What are they? Why do we care about them? When should you use them? And how do they work? Okay, we're going to start with polling. Polling is a little bit like the annoying kid in the backseat of a car. They go, are we there yet? 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 And the driver, in this case, he's standing in for our poor data acquisition device, is going, nope, we're not there. Nope, we're not there. No, I don't have data. No, I don't have data. No, I don't have data. The kid is wasting their energy asking if the device has data. Device is wasting their energy saying they don't have data. It's not the most efficient way of doing things. There are some advantages in that. In this case, the kid is getting to choose when they want to hear if they're there yet. But in the case of a CPU, there are advantages to this. Like there's a reason USB is polled instead of interrupts, but it's not really the best for if you're trying to prioritize something. In the case of USB, I would guess that the primary reason there aren't interrupts isn't because it wouldn't be nice to have them, it's because you have 4 conductors in those cables, and each interrupt usually wants its own conductor. So that wouldn't work once you have 20 devices on there. That's just not physically possible. So that's polling. Now, what's interrupts? Well, an interrupt is literally just what it sounds like. It's interrupting something. So you have an execution path of a CPU. A general 5-stage execution path that's used for teaching these things is fetch, decode, execute, memory, and write back. Now, in the actual CPU and a microcontroller, it is probably far more complicated. I'm not going to try to break that down. It would take a whole nother video and a good bit of research first. So for now, we're going to go fetch, decode, execute, memory, write back. Now, when you do an interrupt, whatever is in there is going to get completely flushed. The data on what needed to be done, the data that it needed to figure out how to perform, its functions, is going to be saved, and then it'll load in whatever code you're interrupting with. Now this is expensive because you have to save all that information. There's register files and all sorts of things, but it's also really nice in that you're able to instantly run your code. So it's the trade-off. Do you need the code to run immediately, or do you want to, let the general execution path go? And in hardware, this looks a little bit like, you can visualize it as if there's an AND gate in this execution path, where whenever you're sending stuff through, it's checking, is there an interrupt? And if there is an interrupt, it stops everything. It's a little more complicated than this. A nice simple example is the Intel 8086 processor, which I've linked a blog post by, let me find it, Ken Sheriff below. I'd highly recommend reading that if you're interested in how it works in hardware. We're mostly going to be focusing on software because we can kind of just go, poof, the CPU magically knows and does things. Yay. But cool, so interrupts allow you to interrupt the CPU, but how do you use them? What are they good for? What are they bad for? All that type of stuff. Well, they're really good for doing short things. So oftentimes you'll just have an interrupt set a flag. You get an interrupt coming that says, hey, there's data ready, and then you'll check the flag itself. This means you don't have to poll a device, which is advantageous because whenever you're having to go to an I/O bus like I2C, SPI, anything like that, whereas whenever you're having to talk to something that's off the physical die of the chip, it takes longer because there's physically longer traces, you can't push as high of data rate, blah, 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 so on and so forth. In this case, once you have that interrupt come in, you're just checking a Boolean value, which is extremely fast. You can also do some calculations in there, but the main thing is you want to keep them short and sweet, because an interrupt is completely taking over everything that's going on. If you have a very complicated function in there, well, all your other stuff that could be quite important isn't running. You don't want to just completely dominate it, and you can't do anything else because the interrupt is potentially, you don't always do this, but you may have even disabled other interrupts and interrupts, so the interrupt can't be interrupted. Because, believe it or not, there's different levels of interrupts by priority. The number of levels you have available is going to be defined by your individual microcontroller, and you could have your interrupt interrupted by a higher priority interrupt. So it could just be interrupt everywhere, and then nothing ever gets done and things crash and explode, and it's really hard to debug because C++ is compiled and then you're looking through hex code files and it's just a nightmare. So basically, you want to use interrupts sparingly. You use them when you want to go fast, and when you need to get data quickly, but you don't want to use them when you don't have to. So all that aside, let's see an example of how we actually would use them. So I'm going to open up my code for Offered, and we're going to look at this interrupt declaration. So this is for our ADC interrupts. So we use ADS 1115s right now, and they're nice in that they have an alert pin. And what that alert pin does is it tells us when they have data ready. So we don't have to constantly pull them, because we can write at something like 200,000 samples per second, and they can only give us data at about 860 times a second. Slight discrepancy there, pulling would make sense. So what you do is you type out this attach interrupt, which is saying, hey, I want to put this in the interrupt service table, which is basically a table that maps when this interrupt goes high, go to this part of the code, and I want this interrupt to be attached to the event when digital pin 40 falls to 0, because you can see the falling on the end. That's saying when it goes, you're on the falling edge. And that thing in the middle, the update analog value flag 1, is a pointer to, let me see if I can find it, this function right here. And all that's doing is setting a flag to true. Well, why would you want to do it that way? Well, the thing is, down in this function, the read analog values, we're doing all this setting values and things, and then we're telling the ADC to do things, and it's a lot of things that could take a decent bit of time. And you should just use a flag, because you're going to read that flag incredibly quickly in your loop, because you're able to loop incredibly fast, and you don't want to do more in an interrupt than you have to. That's just always what you want to do. And so when that fires, it will set that flag, which is declared as volatile. Now, a lot of you may not have seen volatile before. What is it? Why does it matter? When do you want to use it? Well, volatile tells the compiler that your program should never, ever look for the cached value of this. You always need to get it from memory. And that's important because when an interrupt interrupts a process, that previous process doesn't know that a value was changed. It has no context. In the case of our code, we have this data acquisition and saving loop. It goes through and it says, right down here, if analog value flag was 1, then run read analog values. If we let it cache that value, the interrupt would come in, set that Boolean value to be true, it would give handling the processor back to the main code, and the main code would keep on going, reading the cached value, never seeing that it actually is true. It would just always think it's false, we never get any data. That wouldn't be good, so you have to throw the volatile on there. So volatile is a little more expensive in terms of read times and write times, because you have to write and read to memory, but it is absolutely necessary for interrupts or multi-threading. Multi-threading is a discussion for a different day, but it applies there as well. So in conclusion, we can distill down this entire thing into a few rules that you, the watcher, can apply until you know enough about this to branch outside of it and deal with edge cases. When you are trying to figure out if a pin is 1 or 0, it is almost always faster to use an interrupt that then sends a Boolean flag that you check in your loop. There are a few cases this is not the case. Do not worry about them. However, some microcontrollers have a limited number of pins that can be set to interrupts. A Teensy 4.1 allows all of its pins to be used as interrupt pins, and therefore you can use an interrupt wherever you would use a digital read. So rule 1, whenever you're trying to read a digital value, if it is performance sensitive, you should use an interrupt with the shortest possible function available, as in set a Boolean flag. However, if your application is not performance sensitive, try to avoid interrupts. They require the interrupt declaration, they require a function to handle the interrupt, and then they usually require additional logic in the main loop that then calls a separate function to actually do the computations. This is far more complicated than you need for, say, an initial boot up screen that asks you, would you like to write to a JSON file or a binary file? No reason to use interrupts. It's overcomplicating it, making it harder to work with. Remember, number 1 rule, keep it simple, stupid. So yeah, follow those 2 rules and you should be good. When it's performance critical, use interrupts. When it's not, pull. Simple, easy, awesome. Thanks for watching the video. I hope you enjoyed it and have a wonderful day.